We're going to pick up with these as we go through this last section, 7.5. It's just a kind of potpourri of different equations, different techniques that are a little bit more difficult than mainly the equations up here in 7.4 were either linear or quadratic, and there was no requirement for substitutions or anything like that. 7.5, not the case. 7.5, they may be quadratic. Here's one that's quadratic, but we have to make a substitution, okay? Here's one that is linear, but what we'll do is we'll turn it into something that is quadratic. And I say linear, like that's not a linear. If we were to graph those, they're not linear, but the structure is linear. Does that make sense? Like if I did U substitution, that'd be U plus 1 equals like V or something like that. So the structure initially is maybe a linear structure, but there's some techniques and substitutions that we had to make that we were not making in the previous sections. Or there are multiple angle questions. So what I want to do here is start with this first question. It's actually example 3, I think. And it's a multiple angle, okay? But the word multiple might be misleading here because we're taking half of it, right? But I can still say that 1/2 is my multiple. It's my multiplier. It's my scalar multiplier. So we want to solve this, okay? Solve this for theta. And I want to solve, I'll try to be aware of this as we go from example to example, because I know my directions don't have it. So let's solve this on the interval 0 to 360, okay? And then solve for the infinite solutions as well, okay? And as we go through this, what you're going to probably find out is that the actual procedure will do that first, okay? The actual procedure will just structurally solve for the infinite solutions first, and then we have to do a little bit of work to get those broken down to the answers that are between just 0 and 360, all right? So just like always, what you're going to do is you're going to try to isolate the trig function. Okay, so I'm going to try to isolate that. So what's the first thing I would do if I'm going to try to isolate that trig function? Okay, so we're going to add 1 to both sides, so I get root 3. Tangent of theta over 2 is equal to 1. And then you say divide by root 3. And then you can change that to radical 3 over 3 if you want. But does anybody remember off the unit circle, one angle measurement attaches itself to a tangent of radical 3 over 3? Pi over 6. Okay, let's do it in degrees. So 30 degrees. Okay, so we're looking at theta right now. So when I take the tangent inverse here of the left-hand side and the tangent inverse of the right-hand side, we get theta over 2 to drop out in the left-hand side. And on the right-hand side, tangent inverse of 1 over radical 3, you just said was 30 degrees. Is that okay? Now, that's a positive 1 over radical 3. Where else is the tangent function positive? The third quadrant. So if I extend that through, that angle there is also a solution for theta over 2. So that would be 210 in this case, right? Okay, because that angle, that initial angle is 30, and this one with the dotted ray here is vertical to it. Okay, so 180 plus 30. Is that okay, everybody? All right, so that is very similar to the procedure that we developed in section 7.4 with those types of questions. But in 7.4, we were always solving for theta. Now we're solving for theta over 2. So now we have to adjust the procedure. So what you do is that you're going to now add to this the period times k. And what is the period for tangent? Pi. Okay, so just in degrees, then it'd be the 180, right? So those then are two formulas to get us the infinite solutions of theta over 2. But we don't want theta over 2. We're always solving for theta, right? So I need to multiply everything by 2 here. So we get 60 plus 360k. And this here will be 420 plus 360k. Remember, k is an integer. Okay. And that sets up your solutions for your infinite interval. Okay. From negative infinity to positive infinity, your solutions are going to be modeled by 60 plus 360k and 420 plus 360k. But what if k right there was 1? What would that produce? It'd give you an angle of 420, right? Is that the same that bottom one would produce if k was 0? Okay, so these two formulas, they lag behind each other by 1 integer, which means this one here and that one there are redundant. Okay, they produce the same result. So I'm going to just provide an answer of that first one. And the reason I use that first one is because it doesn't matter which one you use, but because the 60 degrees is between 0 and 360 and the 420 is not, I would choose the 60. Okay, and that's like if you were publishing your work, this is the thing that if you're going to do this on a handwritten, like let's say the final, and you write both those answers, I'll give you full credit. Okay, but if you were going to be for whatever reason, publishing a scholarly article, and you put both those solutions in your scholarly article, then some other scholar or mathematician that reads that is going to discredit your work because you didn't realize that those were the same solution. Does that make sense? Okay. So there's importance there in being able to analyze that and say, okay, well, what do these two things mean? Do they ever repeat each other? So I'm going to get rid of that one. Okay, so now if I try to find, so that's the infinite solutions. Okay. Now what we're going to try to do is find the ones that are between 0 and 360. Well, if k is 0, we get 60 degrees, right? If k is 1, we get 420 degrees, right? So we automatically right away get outside that range after k equaling 0. So 60 degrees is the only one that is between 0 and 360. And then this is a rule that will generate all the others. Is that okay with everybody? So I want to demonstrate that real quick. We'll zoom out to 0, 360, and we'll make the did that backwards. That's a little bit better. All right, so if we type in the square root of 3 times the tangent of x over 2 minus 1 what in the world? Oh, I know it. All right. Because of my mode. This just might be easier to mess around with in Desmos. See how, well, is in degrees. That's not the curve that we want. So let's, and I'll mess around with that later, see what the issue is. If we go to Desmos, type in square root of 3 tangent of x over 2 minus 1. And now we'll go do this in degrees, set this up to look at just 0 to 360, but 400 just to get a little bit more visual. We can see there that they're in that interval 0 to 360, there is only one intersection of the x-axis, right? Okay. Now, if this, let's just say that, so if I have x over 2, that's the same thing as 1/2 times x. So let's say that instead of 1/2 x, we have like 2x. Okay. So from 1x to 2x, we push things down. We squeeze it down, right? And when we squeeze it down, more solutions get pushed into this blue interval. Okay. Well, when I go the opposite direction, okay, and my multiplier for this a here is between 0 and 1, that is a horizontal stretch. And you can see now these x values are getting pulled away from the origin in both directions. Okay, so you're getting pulled away from the origin right here on the right-hand side going that direction. And when I get down to 0.5, or 1/2 x, which it won't let me get to, we get one solution right there of 60 degrees inside this region, inside between 0 and 360. So then if I take and write, I'm showing right, like x equals 60 plus 360k, where I'm going to say k, how's that working? Why is it getting that? I don't want to use k. Let's use, we'll see here if that fixes things. C is equal to 1. There we go. So we go from -10 to +10, a step of 1. So what this is going to do for us, if I go down here to KB or C being 0, which is my K value, do you see how that then produces those extra intersections? Okay. Now, if you were to write 420, all right, x equals 420 plus 360 times my constant again, and I move them, are the red line, let's actually change that color to looking for tissues. If you open that closet, there's some in there. But if we move C around, so the red line and the green line here, they start reproducing these same solutions, don't they? So you just see that the red line, or not the red, the orange line is one behind the green one all the time, which is fine because there's no set structure or rule that says, you know, K has to start at 0 or 1 or whatever. You can start anywhere, it's just got to be an integer. Does that make sense on how to do that one? All right. I'd like to go up to this question here. Oh, where'd it go? It's the first one, okay? But we're going to adjust it a little bit. So let's put a line through that one. Let's not do that one. Let's actually go 1 plus sine of 3 theta equals 2 cosine squared of 3 theta. So there's two two ideas here in this problem that I want to target. One is the multiple angle idea that we started on Thursday. Just did another example of, so this will be a third example of a multiple angle. So a 3 theta is the argument. And the other concept that we're trying to target here is the issue between these two sides of my equation. Everything we've done so far has either had one trig function in it, or it's had multiple trig functions, but if it's had multiple trig functions, it's been the same one. So if sine showed up multiple times, then it was sine to the first multiple times, or sine to the first and sine squared, or if it was cosine, it's cosine to the first, cosine squared, right? Now we're seeing a sine to the first and a cosine squared, okay? And we can't do anything with those right now, okay? If you have a very good understanding of what your cosine curve and sine curve look like, you can relate them maybe, but that's very tedious. Even on the simplest questions, that's very tedious. So what we like to do here is see, can I replace one of them with the other? Is there a relationship between sine and cosine? And there should be, okay? But we have to decide which one to replace, okay? Do we have a rule? When I say rule, I'm talking about like an identity that allows you to replace the sine with cosine. Do I have anything like that? Sine to the first with cosine to the first? Or do we have a better rule that allows me to replace cosine squared with something like sine squared? We have that, don't we? Okay. So what I'm trying to get at here is that you'll never, I don't want to say never, but most likely you're not going to replace something to the first power with something to the first power. You are most likely going to replace your items that are squared, okay? So in looking at upcoming problems, if I have something squared and something to the first, I'm probably going to direct my attention to that squared term and try to replace it, okay? So we know that cosine squared cosine squared theta should equal 1 minus sine squared theta, right? Now just be aware that instead of theta now it's 3 theta, but it's the same substitution. So now I'll have 1 plus sine of 3 theta equals 2 times 1 minus sine squared of 3 theta. Is everybody okay with that? Now did that get everything down into one trig function? Yeah. Okay. You can do this now, or you can wait a little bit if you want to, but I'm going to say let u equal sine of 3 theta. And if I do that, I get 1 plus u equals 2 times 1 minus u squared. If that was an algebraic equation, what would you try to do next? What are you going to do next with that thing? Say it again. You could. I don't think that's going to be the most, because eventually if you do that, then you're going to probably want to multiply everything by 2 to get rid of fractions. I'm going to distribute. Now, if these were even coefficients or constants, I would do that division by 2. But now if you have a u squared, you have basically a quadratic equation here now, right? So I'm going to do a quadratic equation. I'm going to factor that, right? So I'm going to get everything equal to 0 here. So at negative 2u squared, it'll be minus u plus 1. Now you factor it. And if I'm going to factor this one, the AC method probably works the best. That's going to give me negative 2u squared minus 2u plus 1u plus 1. Group the first two, group the last two. And that's going to end up with 0. I'm going to skip a step here, but you'll get 0 is equal to negative 2u plus 1. You'll get 0 equal to u plus 1. Everybody in agreement on that? But what was u? Sine of 3 theta. So as I go through, I should probably maybe even solve this for u before I make that substitution back in. That's going to give me u to be 1/2. And it's going to give me u to be negative 1, right? So now, sine of 3 theta is my 1/2. Sine of 3 theta is my negative 1. So then 3 theta, what is the angle that gives me 1/2 back for sine? The sine inverse of 1/2 is what angle? Not 60, 30 degrees. And then I should also have 1/2 in the second quadrant, right? So if I get that 30 degrees there, that better be 30 degrees there as well. So how big would that angle be? 150. So 30 and 150 from that first 1/2. And then when is sine equal to negative 1? Careful. 5 pi over 4 would be over here. So that'd be the y value would be negative 1 there. You know, when is the y value negative 1 on the unit circle? When is the... There it's 0, 1, right? Isn't here 0, negative 1? So there it'd be 270, right? Okay, so the algebra was no different here than what we did in section 7.4. Okay? We had to make a substitution first, which is a little bit different, and that's why this is in 7.5. It's a little bit more difficult equation. Once we do that, though, once we go through the algebra, do the back substitution, we get down to 3 theta equals 30 and 150, 3 theta equals 270. Now we have to address the multiple angle situation. If I go 3 theta, I'm going to write it this way. 3 theta equals 30. 3 theta equals 150. 3 theta equals 270. I'm going to add the period times k to each of those. And then if I solve for theta by dividing by 3, right? All the way through all of those, I get 10 degrees plus 120k. You get 50 degrees plus 120k. And we get 90 degrees plus 120k. Is everybody all right with that? Okay. That will produce, those are your infinite solutions. Okay, that will give you all your infinite solutions when k is an integer. Okay. Let's find solutions on the interval 0 to 360. And we haven't talked about this, and we probably should. A lot of times they'll say the interval is 0 to 360 like that, because sometimes you'll get a solution that is 0 degrees will be an answer, and then they don't want the 360 because it's the redundant or back to the same point idea on that interval. Does that make sense? Okay, so they'll basically say it's the same solution, same answer. So they'll close one of these off and leave the other one open. That's usually how they do it. So, like for instance, if they ask you take sine of theta is equal to 0. Okay. Well, that happens at 0 and 360, right? But if they ask me to do it on the interval 0 to 360 and they leave 360 open, and the only answer they'd want would be 0 and not the 360 because it's open. So that's just it's not a huge deal on a test or quiz. I wouldn't really give you a huge issue with that, but so people always wonder why one of these is open and why one's closed. Okay, so if we want to go from 0 to 360, then what we do is say, okay, well, what do you get if k is 0? Always start with k being 0. If k is 0, I get these three solutions, 10, 50, and 90. Then I'll let k equal 1. If k is 1, I get 130, okay, 170, and then 210. And then we let k be 2. And if k is 2, we get 250, 290, and 330. Okay. If I keep climbing with k, the next one I would get would be 370. Okay. Add 120 to this one, it would give me 410. This would give me 450, right? Why would I not use those? They're outside that interval. Okay, so we stop at k equals 2. And basically what we talked about on Thursday was you always start with k being equal to 0, and you go all the way up to n minus 1, where n is your multiplier for theta. Okay, so this interval here, 0 is less than or equal to k is less than or equal to n minus 1, knowing that k belongs to your integer, so you can only have, like, you can't have k to be like 0.5 or something like that. So then if we graph this, and remember what we started, I'm going to graph what we started with. The original problem was 1 plus sine of 3x and cosine squared of 3x. Sorry, it's 2 cosine squared 3x. So we'd be looking on between 0 and 360, the x values in which those two curves cross. And if we click on this, 10 degrees, 50 degrees, 130, 170, 250, 290, and that is exactly the list that we came up with here, right? Okay, there's a 330 in there I didn't click on. 330, right there. I guess I missed these two, 210, 90. Okay? All right. So some people ask, well, heck, why am I doing all this work if I just graph these and Desmond will give me the answer? If on your final I give you these questions and you have just those answers, okay, so on the final this question is probably going to be like a 10-point question. And if you have just these answers, okay, does anybody want to take a guess on how many points they're going to get out of 10? If you just have those answers? I'd probably give you 1 point. So I want to see all of this work, because that shows me that you know what you're doing. You're not just using the technology to get you there. You got questions on those so far? Example 2 here. Let's do this on. We'll do it in degrees again, and if I know it says in radians. If we're done, we get done with time, we'll change them all to radians. It says solve the equation cosine theta plus 1 equals sine theta. Because there's nothing squared here, this might be a situation where if you are savvy enough with understanding your curves, you might be able to say, okay, I know let's just quickly graph like the sine. If I graph the sine, okay, so that's 90 right there. That'd be 180, and that'd be 270, right? And if I graph the cosine, we know that the cosine is going to start here, and then it's going to pass through there. Just kind of do this in a solid. Get down to our minimum, and then we'll pass up through there and finish at our maximum. Okay, but +1, cosine +1, would actually take this thing and make this point go up here to 2, right? And make this point here at 90 go up to right there. Does that make sense? So would that be showing right there? So the dotted curve is that one, right? And the red one right now is that one. Am I showing right here at 90, at theta equals 90, that they're the same? Does that make sense? And if this one here at -1 goes up 1, so cosine theta +1, right there I'd be showing as well that the sine and the cosine +1 intersect at 180. And then if I move this solid one up 1 everywhere else, then that red curve never crosses the dotted one again. So I've got my two solutions, 90 and 180. And I used my understanding, my visual understanding of the sine and cosine curves. Okay. That can be difficult, though. That can be tedious. Okay. So what we want to do is go through this with an analytical approach. Go through it with some algebra here. Okay. Unlike the other one, okay, the one that we just did, we had something squared so we can make a substitution, right? Here we don't have anything squared. And we know, because in the last one we made the substitution for something squared, there must not be a tool that allows us to replace cosine with sine, or sine with cosine. Does that make sense? Okay. Now we could do this. We could say, isn't the sine of theta the same thing as cosine of like 90 minus theta? We know that, right? But what that does is creates two arguments, and that's even more difficult than having two trig functions. Does that make sense? So we don't want to go that route. We don't want to mess with the argument. We want to leave that theta in both these. Okay? What can I do to generate a squared term? You could do that. You can multiply both sides by something. Multiply the left-hand side by cosine +1. Multiply the right-hand side by cosine +1. But if I do that, I'm going to have now I'll have something squared over here, but I'll have sine and cosine on the right-hand side, and that's going to be as messy. And that might be something that you don't realize until you try it. But we're allowed to do anything that we ever want to, as long as we do it to both sides, right? You could, well, if I do that, then I get cotangent, and I would get cosecant as well, right? And that's going to be, it's basically going to put me in the same situation, just with maybe functions that I'm less familiar with. Can you do that? Okay. If I square both sides, that's going to generate a sine squared, so that's nice. Now, if I square this side, just be careful. Because you got to FOIL it, right? Now it doesn't solve my problem of having two trig functions. But now, can I replace that one with cosine squared or 1 minus cosine squared? That make sense? Now somebody in the last class asked, well, why didn't you replace this one with 1 minus sine squared. Well, if I did that, if I replace this one with 1 minus sine squared, because it's a legal substitution, you still got that cosine to the first, which puts you back in the same conundrum that you had up here. Okay? So we're going to replace this one over here. So we got cosine squared theta plus 2 cosine theta plus 1 equals 1 minus cosine squared theta. What happens with the ones? Cancel, cancel. I'll get then 2 cosine squared thetas plus 2 cosine theta equals 0. And that factors pretty easily, right? 2 cosine theta times cosine theta plus 1. So 2 cosine theta will equal 0, and cosine theta plus 1 will equal 0. So this one's cosine theta will be 0, and this one cosine theta will equal negative 1. In other ones like this, when I get 0 and negative 1 back, or 0 and positive 1 back, I never use the inverse like directly. We are using it, but I just use the unit circle off the top of my head. When is cosine 0? 90 degrees. And that's what your calculator would give you back using the inverse. But is there another place on the unit circle that cosine is 0? 270. When's cosine negative 1? Careful. It's 1 at, so at 180, it's negative 1, right? So those are our answers for theta. Okay. Now, if I were to graph this, and this is the reason a lot of times why I graph things, because you might be overlooking something that we need to pay attention to. This is exactly what I started off at the beginning. If you remember at the beginning, we drew the picture, and so we should have answers at 90 and 180. And we got now answers of 90, 180, and 270. So there's an issue there with 270, and I just moved. How in the world? I just moved this window down to the right spot where I can't grab it anymore. That's stupid. All right, so cosine of x plus 1 and sine of x. Okay, so we got 180, 270, and 90. Okay, and we're seeing here the intersections are only 90 and 180, right? So what happens, and I know I'm in radians here right now, but cosine, if I go cosine of 90 plus 1, does that give me the same thing as sine of 90? It does, right? Okay. Now if I go 180, gives me 0 there, gives me 0 there, right? But if I go 3 pi over 2, which is the 270, do I get two things that are equal? Positive 1, negative 1 are not equal, right? So what's that tell me about 270? It's wrong. 270 does not satisfy this original equation. So 270 is an extraneous solution, okay, which is an algebraic concept from college algebra, right? We have an extraneous solution. Anybody remember the mathematics that we conduct on a problem when we're trying to solve an equation that usually generates extraneous solutions? We did it with square roots. We had root equations. When I got variables underneath the square root, what do I try to do to get rid of that square root? If I had like radical 2x, don't I square that to get rid of the radical? And the squaring process is what generates extraneous solutions. Okay? Did we square in this process? Yes. So that's always something that it's not the object or the objective or the goal of this equation, okay? But it is a procedure, it's a process, it's a concept that we've learned previously in other courses that we need to always carry with us. And you always need to remember, okay? It's kind of like if I see x squared or something squared, I need to know that means I need to factor that equation, okay? You also now need to know that, okay, well, when I square something on myself, on my own, then that's going to probably produce extraneous solutions, and I need to check then when I'm done. All right? No new homework. See ya.